All right, today we are going to peel back the plastic on your charging cable and look deep, deep inside the wires. We're getting into the fundamental physics of electricity, the science that powers literally everything we do. So let's follow that spark and see where this story takes us.
I mean, think about it. You do it a dozen times a day and probably never give it a second thought. But have you ever actually stopped to wonder what is going on in that split second? What invisible force just springs into action to light up your room? Well, it's way more than just a simple on-off button. It's really the start of this incredible high-speed journey. So that's what we're going to do today. We're going to follow that electrical journey from its very first push all the way to its final destination. Okay, so every journey has to have a starting point, right? And a reason to even begin. For electricity, that reason is a fundamental force, a kind of push and pull that gets the whole thing moving. It all kicks off on this invisible stage, let's call it, known as an electric field. Just imagine it's an area of influence. Any charged particle that wanders into this field is going to feel a force, a nudge, telling it which way to go. This field sets the entire stage for the journey. So how do we actually measure that initial push? Well, it's called potential difference, but you and we just call it voltage. Voltage is basically the amount of energy given to each little bit of charge to get it going. Think of it like electrical pressure just building up, waiting to be released. And this slide, it breaks it down with the official definition. 1 volt is the energy, that's 1 joule, that it takes to move a specific group of charges, that's 1 coulomb. But here's the real takeaway. Higher voltage just means a way stronger push for every single charge in that wire. Simple as that. Okay, so we've got the push. Now, what about the flow itself? Once all those charges are actually moving, we need some way to measure the traffic on this electrical highway.
And that's what we call electric current, measured in amps. So if voltage is the push, then current is the actual flow. It's like we're standing by the side of the highway counting cars. Current tells us exactly how much charge is zipping past one single point in the wire every single second.
But here's the thing, this electrical highway, it is not always a smooth, open road, not at all. In fact, every wire, every material presents its own kind of obstacle course for the current. And that brings us to our next big idea. This opposition is what we call resistance, and we measure it in ohms. It's the constant pushback, the friction against the flow of current. And this famous formula you see here, Ohm's law, it pretty much defines the relationship between our 3 main players. It's the physics of the constant battle. Voltage pushes, resistance pushes back, and the current is what we see as the result of that whole struggle. Which leads to a great question, right? Why are some materials, like copper, so easy for electricity to travel through, while others are incredibly difficult? Well, it really boils down to 3 main things that decide how hard this obstacle course is. First off, length. Pretty straightforward. The longer the wire, the more stuff the current has to navigate through, so more resistance. Second, the area, how thick the wire is. A thicker wire is like a wider highway. It's just easier for all that traffic to flow, so there's less resistance. And finally, the material itself. Some materials are just naturally easy superhighways, while others are more like a bumpy, unpaved road.
Now, in a perfect world, resistance would always be constant. When it is, we call that an ohmic conductor. But in reality, a lot of things are what we call non-ohmic. A perfect example is an old-school filament light bulb. As it starts to heat up, its resistance actually goes up. The obstacle course literally gets harder the more current you push through it. So, we've talked about the push, the flow, and all the roadblocks. But wait a minute. Where does the energy for this whole trip even come from? Let's go all the way back to the beginning, the power source itself. Okay, this is a really crucial difference. A battery has what's called an electromotive force, or EMF for short. This is its total, ideal, 100% energy potential when absolutely nothing is connected to it. But the second you plug something in and current starts to flow, what you actually get is the potential difference, or voltage, which is the energy being used out in the circuit. So you could say the EMF is the promise, but the voltage is the actual delivery. So why the difference? What's the catch? It's because the power source itself isn't perfect. It has its own tiny internal obstacle course. This internal resistance uses up a little bit of energy before that energy ever leaves the battery. You can think of it as this unavoidable energy tax on the whole journey. All right, we've covered the start, the flow, the challenges. Now for the payoff. What is the entire point of this electrical journey anyway?
Well, it's to do useful work for us. And that finally brings us to power, measured in watts. Power is the rate at which all that electrical energy gets transformed into something else. You know, the light from a bulb, the heat from a toaster, the sound from your speakers. It's the grand finale of the entire journey.
And this is where it all comes together in the real world. For a toaster, we actually want a really difficult obstacle course. We choose a material with high resistivity, like nichrome, because its whole job is to turn electrical energy into heat. But for the wires in your wall, we want the exact opposite. We want something like copper with super low resistance, so all that energy gets to its destination without being wasted as heat along the way.
So the next time you plug in your phone, just remember the incredible journey that's happening inside that cable. A powerful push from the source, a massive flow of countless charges, and this constant battle against resistance, all just to bring your screen to life. It is a complete journey of physics right there in the palm of your hand. So which part of that journey are you going to think of first?